Good morning. So I'm Mathieu Fauvel from CSBio Lab, and I'm going to present what we did in ANITI 1 about how to analyze satellite images. Okay, so this work was done in the chair of Nicolas Daubijan, learning with little complex data, little or complex data. And in particular, we work on 3 points. The first one was how to combine physical models about our processes and artificial intelligence. Also, we face some noise in the data. I will show it later, but so learning with noisy data, either from the input and from the ground truth also. And in particular at CSBio, we are working with multi-source, multi-scale time series, so how to process them effectively. People involved in this work was mainly from CSBio, so myself, Lordine Glada, Julien Michel, and Sylvia Valero. And within ANITI, we have 2 PhD funded by CNES and the region, and also CS Group. So I'm going to present the work of Yoel Zara and Valentin Bellet. Okay, so what we try to do at CSBio is to extract some information about the Earth observation. So you have 1 images here. This is an unscale images, but we can zoom in and we have a spatial resolution on 10 meters. So we have, let's say, good details about the ground surfaces. And we try to infer some information about the land cover, the land use, some biological information such as biomass, chlorophyll content, etc. And we do static analysis and dynamic analysis. In particular, we try to find where there are changes on the Earth. The problem, first problem, is that we have some noisy data because of clouds and shadows and atmospheric effect from different seasons. So we have most of the images with no data. The white area is the clouds. And so we need to develop algorithms that are robust to this, let's say, irregular sampling of the Earth. So we try to include some physical model from the acquisition process, but also from the observed processes such as vegetation, growth model, etc. And try to combine this with machine learning, data science. So today I will present 2 work made by, Valentin Bellet about how to use some physical prior information for the classification of land cover. And the second work, which is similar to what Serge discussed a little bit before, how to use autoencoder and a physical model to define, let's say, a latent space that suits the physical models, and well, try to learn everything with a reduced training set. So let's say I try to show some example about the data we have to process. So here this is the X star. So this is 1 pixel acquisition for 1 year. So you have the date of the year here. And here you have the features, so the channels. Okay, we have more channels than for color images because we have several spectral wavelengths. But well, in gray you have the missing data. So missing data is because of clouds, because of the orbit of the satellite. And depending on the pixel and its location in the, let's say, France territory, we have different acquisition patterns. So we need to find an algorithm that is able to deal with irregular temporal sampling, but also with unaligned acquisition. So we have different acquisition time between pixels. So our strategy was to try to define latent space that take into account the structure of the data. So we use a random matrix modelization. And well, in the latent space, we want to have a fixed and constant representation. So we do 3 things. The first thing is to, let's say, define a temporal interpolator on the latent date that will be learned during the training process. And well, this is a very conventional kernel interpolator, but for the kernel here we use temporal attention to take into account that according to the season, we have different level of noise in the data. We have more noise during the winter than in the summer, and well, using this temporal attention, we are able to model the different level of noise for the interpolation. Then we take into account that the phenology, that is the reflectance of the pixel along the time, can be different according to the spatial position because of sun exposition, temperatures. The vegetation can grow differently in the north or in the south of France. And to take into account this phenomenon, we use, this is very conventional, but we use spatial positional encoding, sorry. And lastly, we add the last layer to take into account the correlation in the spectral domain because we have some redundant information. Okay, so in this latent space, finally, what we get something that take into account the spectral structure of the data, so information provided by the structure of the vegetation of the land cover, let's say. We have also a part of this modelization that take into account the spatial position, are the pixels close together or not, and the last term, which is interaction between the spatial position and the reflectance of the pixels. Okay, so this is for the construction of the latent space, and then we use the conventional end-to-end approach with a Gaussian process classification algorithm to learn in an end-to-end way all the parameters of the model. So the latent representation with as input irregular and unaligned time series. Here we have a fixed representation, and then we have the classification. So we end up with a kind of loss function which is very similar to what we have in a variational autoencoder. We have a regularization term and a term that is well, which is the loss regarding the wrong or good classification of the sample y here. So I won't get into much detail, but we can solve these kind of things using similar approximation that is done in a variational autoencoder. We perform some experiment at large scale. So this is the well, this is the France, this is the south of France area. We took pixel from all this area. We also take 1 year of data, so it's about 300 dates with images with 13 features. Well, this is well, I'll go to the result directly. Well, and in terms of results, this is what our lab produce each year, a land cover map of the France that is freely available using a very, let's say, old-fashioned approach where we first interpolate linearly all the temporal acquisition onto a regular grid and then apply the random forest classifier. So this is the baseline, and this is what we get when we jointly learn the latent space and use a Gaussian process. We get a significant increase of the classification accuracy, that is a number of well-classified pixels. We compare this with also using a standard deep learning, deep networks, for instance, but we get less good accuracy. So if you want more detail about this, you have the publication of Valentin here. So second result about how to use some physical models to infer biophysical parameter. So conventionally, in remote sensing at least, when we try to recover some physical variables, we have some regression approach. So this is very standard. We have our model, we have the satellite observation, we have some ground truth data, and we try to learn how to regress from the satellite observations the physical variables. The problem in practice is that this ground truth is very difficult to obtain, in particular at large scale, because we need either to go in the field with some materials and to do some field survey. So this is costly in terms of time, in terms of human skills, in terms of money also. So sometimes we can also use physical models to generate some ground truths and then use then try to learn the regression function using this simulated data. But there is also a problem because the physical model is usually an approximation of the reality, and also the second problem is how to select the distribution of the physical model parameter to get some realistic simulation. So to try to remove these two issues, we propose to use the physical model in an autoencoder scheme. And in particular, we propose to remove deep network from the decoder and to replace the decoder by the physical model. The name is ProSail here. And the tricky part will be to encode the latent space with which respect the physical meaning of the model parameter. So in particular, we need to have a specific range of variation for data, positivity, sum to 1, for instance. And also we have some order condition for the parameter. So let's say we have the growing season that come before the senescence, etc. So we need to define a sampling strategy that respects the latent space let's say physical model parameter configuration. Once we have solved this, we can learn everything without any reference data. So it's a very good thing for a practical situation because we only need satellite images. And satellite images, we have a lot of data available from the European Space Agency or from the CNES, for instance. So we can learn very efficiently this kind of model. Just some result to show the improvement with respect to what it is done actually in the European Space Agency. So the European Space Agency used the regression framework I discussed just before. So this is different location seat. This is two features, so leaf area index, so the proportion of leaf in the pixels, and CCC is the canopy chlorophyll content, so the level of chlorophyll in the top of the canopy. So what ESA, European Space Agency, do is just they fit one model for every site location and optimize everything side by side. So this is very long. And with our approach, using only remote sensing images, no ground truth, when we compare with, of course, ground truth data, we get similar result or a much better result. So finally, this is very convenient. We have because we use no training data. And another byproduct, so this is one example of leaf area index. Since we use a variational autoencoder framework, we can also generate variants of the estimation that can be propagated into agronomic model or ecological model if needed. So in conclusion, at least for us, using this kind of generative models and deep learning model for satellite image analysis, it's good things because we are more robust to noisy data, noisy of input data, but also noisy data from the ground truth. We can learn model, we can learn a model without any training data and still have a very good result in terms of accuracy. And perspective, which are in ANITI 2, is to use more data source. In the result here, we use only one data, Sentinel-2, but we have many satellites in orbit, and we can combine different sources of information with different modality. We need also to work with more complex physical model. Here, it was easy because the model is derivable. So we don't have any issues regarding that. But for meteorological model or agronomic model, there are some of them are not derivable, so we need to find some solution for this. And it should be an industrial share, but let's see. Thank you.
So talking about the non-differentiability of your model, so it makes first order method difficult to use in this situation? Do you have an idea of what you would do? Ah, I n'ai pas entendu. Okay.
The first things we are going to try is to do some model approximation. We can learn neural nets to approximate the model and then use this neural net in the backward and forward path. That not necessarily smooth, but close enough to the physical model.
Thank you, Mathieu.